Thank you. Welcome back to our video and our 8th video on derivatives, where we will be talking about optimization. First, before we start anything with optimization, we are going to talk very quickly about Extrema and the second derivative test. So, an extremum is defined where the derivative of a function with respect to x is equal to 0. This is also called the critical point. And for a simple example, such as the function f of x is equal to x squared, as you can see right here, d dx of x squared equals 2x, and then the extremum, the critical point of this, is when the derivative is equal to x, is equal to 0, sorry. So x is equal to 0. That's the critical point. And then from there, you can go on and plug this into the function to determine what the output is. And then the second derivative test. So the first derivative test, you can find out what critical points a function has. However, it doesn't tell you whether it's a maximum or a minimum. What tells you what is a maximum or a minimum is the second derivative test, where if you take the second derivative of a function and evaluate the second derivative at the critical point, if the second derivative at the critical point is greater than 0, it's a minimum, and if the second derivative of a function at the critical point is less than 0, then it is a maximum. And if it's equal to 0, it's a point of inflection. So it's kind of something like this, where we have a positive second derivative here. Here is our point of inflection, and here we have a negative second derivative. And you can see negative second derivative. Around here is the maximum, around here is the minimum, and that's a positive second derivative. So with this in mind, we are going to perform a sample problem of determining the extremum of a function. Okay, so our first example is f of x is equal to 4x minus x squared minus 5. So first we want to find out what points are extrema in this function. So what we have to do is take the derivative, the first derivative of df dx. And that's equal to 4 minus 2x. And if we remember from earlier, a point is an extremum, or a critical point, if the first derivative is equal to 0. So we have to set this derivative equal to 0 to determine where, the value of x where we have a critical point. So we solve this. 4 equals 2x, x equals 2. So now let's determine whether it's a maximum or a minimum. So how are we going to do that? We're going to find the second derivative. So d2 dx2 is equal to, it's the derivative of this. So the derivative of 4 is 0. The derivative of negative 2x is negative 2. And now we have to find the second derivative at x equals 2. And we can see that the second derivative is just a constant. So the second derivative never changes. So in this case, the second derivative is negative. So this at x equals 2 is a maximum. Now the next point is to find out what f of 2 is. So that's equal to 4 times x equals 2 minus 2 squared minus 5 equals 8 minus 4 minus 5 equals 8 minus 4 is 4 minus 5 is negative 1. Okay, so we're going to be doing a couple optimization problems now, where we're going to be taking advantage of these critical points. So, by the way, these problems are being taken out of the Hughes-Hallett 4th edition Calculus Single and Multivariable. In case you wanted to look along. So this first problem is problem 19 on page 187. A grapefruit is tossed straight up with an initial velocity of 50 feet per second. The grapefruit is 5 feet above the ground when it is released. Its height at time t is given by the following function. Y equals negative 16t squared plus 50t plus 5. And what we're trying to find, how high does it go before returning to the ground? So we want to find out where its maximum point is. So first let's find the critical point. So the critical point is when dy dx is equal to 0. And dy dx is negative 16t squared. So the derivative of negative 16t squared is negative 32t plus 50. And then we solve for this and we end up getting time is equal to 1.56 seconds. Now we can see that this is a maximum, but let's just run the second derivative test just to make sure that it is a maximum. So we find the second derivative of this function, so that's the derivative of this d squared y dx squared is equal to the derivative of this, negative 32t. The derivative of negative 32t is negative 32, and the derivative of 50 is 0. So the second derivative is negative 32. Negative 32 is less than 0, so it is a maximum. So the last problem is the following problem. Problem number 20. When you cough, your windpipe contracts. The speed c with which air comes out depends on the radius r of your windpipe. This is lowercase r. If capital R is the normal rest radius of your windpipe, then for r is less than or equal to r. Okay, so little r is defined as the radius. And capital R is defined as the rest radius. And little r is less than or equal to big R. Then the speed, v, is given by a times r minus r times r squared, where a is a positive constant. And what this problem is asking is what dosage maximizes the temperature change. Sorry, what value of r maximizes the speed? I was reading the wrong problem, I apologize. So, what value of r maximizes the speed? So we want to find dv dr. And we set this equal to 0. And we perform the chain rule. So, not the chain rule, the product rule. So we can keep the a outside because this is a constant. But we want to find the product rule of this. So we take the derivative of the first times the second. So the derivative of the first is -1 times the second, which is r squared, plus the first, r minus r, times the derivative of the second is 2r. Now because this is equal to 0, we can just get rid of this a. And we end up with r squared equals 2r times big R minus little r. So by looking at this, we can find that there are two critical points. One of these when r is equal to 0, but later on we'll be seeing why r equal to 0 is not the maximum. And the other we can find by getting rid of these r's. So we have r equals 2 times r minus r. R equals 2r minus 2r, little r. Little r equals 2r over 3. So let's plug these into this expression. So when r is equal to 0, the velocity is 0. When little r is equal to 2r over 3, let's find out what this is. V equals a times r minus 2r over 3 times 2r over 3 squared. r minus 2r over 3 is r over 3. So this is equal to a times 2 times r over 3 times 2r over 3 squared is 4r squared over 9 equals a times, this is a, times 4r cubed over 3 times 9 is 27. So let's just rewrite this out as 4a r cubed over 27. And that is the maximum velocity. So thank you for watching our video on optimization. Please come back for our next video on rates and related rates. And then afterwards we will be discussing the fourth and final video on the applications of derivatives in L'Hopital's rule. So thank you for watching. Please subscribe if you haven't already, and I look forward to seeing you in our next video. Goodbye.